Hello everyone, welcome back to Alkaline Hydroxide 784, and today in the chemistry series we are doing reaction kinetics. So let me just say that this is probably one of my more favorite or at least preferred topics, at least especially now because I have to do a lot of it, so I'm pretty familiar with it. Yeah. So this might probably be one of the things to take note of, especially if you're gonna do chemical engineering in the future. Yeah, you must definitely remember this topic. It's pretty useful for that. Okay, so let's start, and yeah, hopefully this won't take too long. Okay, so the first learning outcome is about these terms, the rate of reaction, rate equation, blah 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 blah. So yeah, there's a lot of terms. Okay. So what's the first one is the rate of the reaction. So what does it mean to have a rate for a reaction? Well, just referring to the speed at which the reaction proceeds. And of course that doesn't really make sense because usually when you think of speed you think of a car going fast or something. So how do you quantify that for a reaction? Okay, so the way they do it is in a reaction we look at the concentrations of stuff like the different reactants in the solution, and the rate is depending on how fast the concentration changes. So the rate is referring to the rate of change of concentration of the reactant or the product. Yeah, so that's the rate of reaction. So how do you figure out the rate? I mean, technically if you want to do it experimentally, you just take the change in concentration and then look at the gradient part of it. But if you want to write an equation, the rate equation, you would be writing like the rate equals to K times whatever concentrations you're looking at. So it just states the relationship between the rate and the various concentration at that point of time. Okay, so order of reaction, order of reaction is basically like a power. So let's say if it's a reaction is first order, it means that the rate equation will have that particular, okay, if it's first order with regards to a particular reactant, that reactant will only influence the reactant, sorry, the rate proportionally. If it's like second order, then it will be proportional to the square of the concentration, and so on and so forth. Okay, so rate constant. So rate constant is the K, which is what we see as the constant of proportionality in the equation. So that's the K. And the half-life of a reaction is the amount of time it takes for the concentration to decrease by half. Yeah, basically become 50% of what it was originally. So rate determining step, it is the step in the reaction. If you're looking at multiple steps, is the step that is the slow step, and therefore is the main rate, the main step that determines the rate. If it happens really quickly, then the rate isn't really affected by those steps, but if it's a step that goes pretty slowly, it is the one that limits the rate in a way compared to the fast steps. So activation energy is the amount of energy you require to start the reaction. And catalysis is enzyme catalyzing, sorry, not enzyme, any kind of catalysis. Basically it's making the rate faster by providing an alternative process that requires less activation energy. Okay, so let's move on to the second learning outcome, and you can learn more about these terms as well. Okay, so the second one is the construct and use rate equations of the form rate equals to K, concentration of A to the power of M, concentration K. So this is referring to a reaction where you have A plus B becomes products. So in this scenario, the rate is dependent on A and B, the concentration of A and the concentration of B. So yeah, you can have in A levels we don't really go too far off in terms of the order here. So In A levels, we're limited to simple cases of single-step reactions or of multi-step processes with a very clear rate determining step, for which M and N are 0, 1, or 2. So you look at the different examples here, and if there's anything to explain, I'll explain it. So how do you deduce the order of a reaction using the initial rates method? Yeah, so there's different ways of determining the order or the rate or anything else. Okay, so the equation I told you would usually describe a reaction where you have A and B become a product. Okay, so if you're using the initial rates method, you can look at the data that's provided in the question, or if you're doing an experiment, look at the data that you collected, so you better do that properly. Yeah, not kidding. Okay, so if you're doing it in the theory paper, you probably have to draw a graph, maybe. Like you still have to draw a graph sometimes to determine the reaction. But if you're just looking at initial rates, you can, if you have a table, you can see, oh, if changing the concentration of A, for example, by 2, like the initial concentration, leads to an initial rate increasing by 2, it means that the concentration of A is proportional to the rate. So that's what the initial rate method is about. So you're looking at the initial gradient of the graph. Yeah, so you can even do this with a graph, or if it's written in a table, you can use that information from the table. So for a graph, it would be mostly like you first plot the rest of the points, and then you continue the graph to the end, and then you draw a gradient from t equals to 0 in order to see what the rate is. So you find the gradient, and that's the rate. So yeah, okay. Okay, so the second one is justifying for 0 and first order reactions, the order of reaction from concentration time graphs. Okay, so this is what we have here. If we see that the graph is straight to begin with, there's no curvature in the graph. It's just a straight line going down. Like, it looks like a y equals to negative x graph kind of thing. Then it's a zero order reaction because the reaction is not affected by the change in concentration of A. Because you're looking at concentration time graph. So the concentration of A is decreasing, but the gradient is the same. Yeah. If you're looking at the first order reaction, we can find it through the fact that the half-life is consistent. So what that means, you can pick a point on the graph and then find the number that's half of that concentration that you picked out, and then you repeat that for another set of concentrations. So it doesn't have to be the initial concentration, it can be any concentration that you can clearly find the half of that concentration as well. If it's out of bounds of the graph, then probably don't use it. So if you do that with two different concentrations and you find the exact same or almost similar time half-life, because experiments are not like 100% gonna be the exact same half-life, but if you do get the exact same half-life, then good for you. Then that you can conclude that it's a first order reaction. Okay, so verifying that a suggested reaction mechanism is consistent with the observed kinetics. Okay, so for this one is you will get a multi-step reaction, and you can see, you'll probably know which one is the slow step. So once you know what's the slow step, you can try to work backwards and then see whether this corresponds with the observed kinetics. So how you do that is, if you have like 3 equations, for example, and the second one is the slow step, you first write a rate equation for that step, assuming that it is first order with regards to that equations alone, because we already broke it down into elementary steps, so you can say that it's first order for each of the reactants. And then from there, if there's a reactant that doesn't look like the original reactant, then you have to go back to the first step and then change that in, like, see what created that reactant and find the write a different rate equation for that part itself, and then you sub it in, and then you get the final rate equation. I hope I would have demonstrated that properly here, but let's see. Okay, so from there you can get the overall rate equation, and then from there you can compare it with the observed kinetics and see whether it's the right equation, or whether they both match. Okay, so the next one is predicting the order that would result from a given reaction mechanism. Okay, so yeah, it's the same thing. It's just that you don't need to compare it with anything else. So you just do the same thing, and then you predict what's the order of the reaction by seeing the overall power of all of the reactants in that particular rate equation. And the last one is calculating initial rate using concentration data. So what I mean here is what I said at the very beginning here, which was to do the grafting and then calculate the gradient at t equals to 0. Okay, so the reason why this is supposed to work is because if you look at the concentration, and if you look at the volume of the reaction, we are assuming that the volume is going to be somewhat constant throughout the entire reaction. So the concentration is the only thing that we are changing here throughout the reaction. And the time equals to 0 part is like, it's a very small change in time, so we're assuming that whatever the graph we get there is going to be equivalent to the initial rate of reaction. Yeah, so you can assume that with a very small change in time and a very small change in and virtually almost no change in volume, you can assume that the change in concentration at that point of time is going to be the initial rate of reaction at t equals to 0. Yeah, that's why we can do this. Yeah, great. So the next learning outcome is about the half-life of a first order reaction. So the half-life in the first order reaction, as I mentioned earlier, is always constant. So it is constant no matter what concentration A is or B is, or whatever it is. Okay, but half-life is only in a first order reaction. So if it's second order, then your half-life is no longer constant. So for your first order reaction, you can have a half-life that is maybe, let's say, 20 seconds or something, and let's say your initial concentration is 50 milligrams per, I don't know, dm cube. Okay, actually that seems quite small. Okay, anyways, 50 milligrams per dm cube. and then after 20 seconds it becomes 25 milligrams, then after another 20 seconds it becomes 12.5, then after another 20 seconds it becomes 6.75, and after that I don't remember how to calculate. Okay, I mean, I'm just saying this off the top of my head without even using a calculator, so yeah, you get the point. And even if the concentration goes to, like, I don't know, 0.0001, it will still decrease by half in that 20 seconds. So in a way it never goes to 0. Like, the concentration will never go to 0 if you think about it that way. And there will always be a little bit of the reactant left. That's why we don't really care about the end of the reaction, more like 99% completion of the reaction. Especially in uni applications, sometimes we just look at the 99% mark, not really fully complete reaction. Yeah. But anyway, that's not really the most important thing here. Just know that it's always constant. And so how do you find it? You can just, the half-life is ln 2 over k, and k is ln 2 over half-life. If you need to know why, I can show it to you. There's a very simple way of showing it. It's actually just calculus in the end. Like, once you go to uni, that's pretty much all you do. You just do calculus. Especially if you're doing engineering, you have to just do like the idea is that you write the dA or dt, or sorry, d concentration of A or dt is equals to k concentration of A, right, as you see in the rate equation. And then if you do the integration thing, it's like solving differential equations. Oops. Yeah, if you solve the differential equation, you will then find out that it is a exponential equation, and from there you can obtain ln 2 over k is equal to your t half. Yeah. Yeah, that's pretty much it. Okay, so now let's move on. So how do you calculate the rate constant? First calculate your, if you are using initial rates method. Okay, so initial rates method is what we looked at earlier, knowing what the initial rate is and then finding the order of reaction. And then from there, if you have the initial rate and you have the initial concentration, then you can just divide and get your constant. Yeah, get your K. Okay, so the next one is devise a suitable experimental technique for studying the rate of a reaction from given information. So this is what I mentioned just now. The idea is that you first run, like you get the data for the concentration at various points of time, and then from there you can get your initial rate, right? So how do you get all of that data? Well, that's the important part, because that's what you talk about in your chemistry practical, or maybe, I don't know, actually mostly in practical. So for that, you need to be able to measure the concentration or some kind of parameter at certain points of time. And I think I would have mentioned this in greater detail in my chemistry practical series, so if you want to check that out, you can. I think it's the one with the kinetics and energetics, that episode. I don't remember which one it is. So the idea is you calculate a certain parameter which is proportional to concentration. Like it doesn't have to be concentration itself. Like for example, if your reaction releases carbon dioxide, then you can just measure the amount of carbon dioxide released at a point of time. So that's actually the product. So you can measure the concentration of the product. But you have to know that when you're measuring the product, it's a bit different from measuring the reactant. The reactant will be decreasing, the product will be increasing. So for example, your T half would actually be the amount, like maybe from 0 to 50%, then from 50% to 75%, then from 75% to 87.75%. Is that correct? I don't know. 87.5%, sorry. And so on and so forth. Yeah, so you had to do it the other way around, if you know what I mean. Yeah, so it's like a 1 minus the exponential rather than just the exponential. But if you're able to measure the concentration of the actual reactant or measure the pH, then you can do it directly for the reactant itself. So it depends on the reaction that you're looking at, and it depends on how the entire experiment is conducted. So for that, you should probably just look at the practical series instead. Yeah. Or just have a good idea of how these experiments are done. So explain qualitatively in terms of frequency of collisions the effect of concentration changes on the rate of a reaction. Okay, so what this is referring to is like, it's a bit like kinetic particle theory, but yeah. Okay, so when you increase the concentration in the solution, I guess, the molecules can collide more frequently. Yeah, that's pretty much it. But it's not just about more frequently. There's also a greater chance of better orientation, like they collide in the right orientation such that reaction will occur and not just have them bump into each other and waste their energy. I don't know. So I'm pretty sure there's supposed to be more words than that, but that's the gist of the entire explanation. So you must make sure that if the concentration is increased, there's more of those particles or molecules in the solution itself within the same amount of volume, and therefore they have lesser space to move, I guess. But and they're more likely to collide with each other, and because of that, there's a higher frequency of effective collisions, which means right orientation and actually colliding in a way and creating a reaction. So the reaction will happen a little bit faster because there's a higher frequency of collisions. Okay. So now we will look at what activation energy means using Boltzmann distribution. Okay, so activation energy, as we have learned many times, is the energy required to actually kickstart the reaction in a way. So Boltzmann distribution is this graph which shows the overall energy of all of the particles in that, the solution or the reaction or whatever. So the graph will have like a peak at a certain point, and then it will decrease gradually, like exponentially towards the end. So there will be some particles that have a much higher energy than the rest, and they are the one that can undergo the reaction because they actually have more energy than the activation energy. So in order to represent this, we just draw a line at this point, and then we say, oh, this is the activation energy, and only the particles that are above that particular point can undergo reaction. So that's how it works. Yeah. So the rest of the particles, which is the majority of them, don't undergo reaction immediately. That's why there's a rate to begin with. If not, the rate would be infinite. They will immediately have reaction. So how do you increase the number of particles that can quickly get reacted in a sense? We can we'll look at the temperature change, and yeah, we look at temperature change first. So temperature change, you have to use either collision frequency or Boltzmann distribution. So if you use collision frequency, the temperature change means like if you increase the temperature, if you increase the temperature, the particles will move much faster. So they will have more they'll have more collisions, like increased collision frequency, and of course increased frequency of effective collisions, aka the right orientation and all that stuff. You get the idea. So the rate is going to increase because the rate constant itself increases. It's not the concentration that has changed, but the actual rate constant has increased because the temperature has increased. So the rate constant does depend on the temperature. If you're describing in terms of Boltzmann distribution, you can look at the Boltzmann distribution. So when the temperature increases, the energy of all the particles is going to increase, like in a way, to some extent. So it's like you shifted the graph a little bit to the side, and there'll be more particles in that have an energy greater than activation energy. So that's why there's a higher rate in the sense, and the rate constant is higher as well. Okay, so the next one is about catalyst. So how does the catalyst affect the rate and rate constant as well, and how you view this on the Boltzmann distribution? Okay, so in the catalyst, as I mentioned earlier, the catalyst does its job by allowing the reaction to proceed using a different pathway or different mechanism which has a lower activation energy. So this means that the rate constant will actually be larger because it's dependent on both temperature and activation energy. If you're looking at the Arrhenius equation, I think that right equation, I don't know. Anyways, but just know that it depends on those two things, but not really on other things. So yeah. That you don't need to explain collision frequency. Just say that the activation energy is a different, because the mechanism is different. It has a lower activation energy, and the rate constant is higher now. Yeah. And once again, this doesn't affect the concentration. It only affects the rate constant itself. And if you look at this in terms of Boltzmann distribution, how do you show that? The curve with the energy of the molecules is the same, but the activation energy line is the one that moves this time. So it will move towards the left a bit, and therefore more molecules, even though the energy hasn't changed, they now have a higher energy than the activation energy. So yeah, the rate is higher. Simple as that. Okay, and rate constant is also larger in the sense. So the next one is outlining the different modes of action of homogeneous and heterogeneous catalysis, including the Haber process, the and so on and so forth. There's a lot of stuff here. The only thing is I have a feeling I do not remember what catalyst is used. And that is pretty important to know which catalyst is used in all of these processes. Yeah. So the Haber process is the one where you make ammonia. Yeah. So you make ammonia and I think you need like zinc or something. Wait a minute. Okay. I'm just gonna quickly figure out what the catalyst is. Oh yes, iron. So the Haber process takes place at 400-ish degrees Celsius at 200 atm with an iron catalyst. So how would we describe the iron catalyst? Because you know you have either homogeneous or heterogeneous. So homogeneous means that it's at the same phase as the other reactants, and heterogeneous means that it is at a different phase. And in this case, the iron catalyst is solid, so yeah, it's gonna be at a different phase compared to the nitrogen and the hydrogen, which are obviously gases. Yeah. So how this works is you know, if the iron catalyst is there, then the nitrogen and the hydrogen will then have like this adsorption onto the catalyst, and then by absorbing onto the catalyst, it's a different mechanism already, right? So the bonds between the nitrogen and hydrogen are weakened, and therefore nitrogen can bond with hydrogen much more easily, and then they can you know it'll become ammonia. But the funny thing about this whole process is that it's reversible. So the idea is if you keep removing the ammonia, then you can probably push the equation forward. Yeah. And that's because yeah, you know why, in a way. If you remove the product, the equation can move a bit forward. And we look at that in chemical equilibria, which is the next episode. Okay, so the next one is the catalytic removal of oxides of nitrogen in the exhaust gases from car engines. Okay, so this one I kind of know. This one is that they use like those fancy metals like platinum and all. So you know the car engine has this thing that removes all these greenhouse gases, or at least converts them into less harmful greenhouse gases. So you know you reduce the greenhouse effect a little bit, hopefully. Yeah. Oh man, I talked too much already. Okay, um so what happens is that the NOx, basically the nitrogen oxides, they go into the I don't know what that thing is called. Is it the carburetor? Yeah, they go into that thing, and once again they adsorb onto the surface, and they're compelled to become stuff like nitrogen, or if it's something like carbon monoxide, it becomes carbon dioxide, maybe, I don't know. So yeah, you can just describe it in that way. This is once again heterogeneous, so because the metals are solid and the nitrogen and all that stuff is gas. Okay, so catalytic role of atmospheric oxide of nitrogen in the oxidation of atmospheric sulfur dioxide. So in this scenario, we see a homogeneous catalyst because the NOx is also a gas and the sulfur dioxide is also a gas. So what happens when NOx goes into the atmosphere is that yeah, it just does. I kind of forgot the exact reaction, but if you let me just search it up because I don't want to say wrong things. Yeah, NOx make. Okay, so I think it's something to do with radicals because yeah. Okay. Okay, never mind. This is too troublesome to search. Okay, so uh, so basically the NOx goes into the air, and originally the you know all the ozone and everything is just okay. Actually, the ozone is a different thing. It's something to do with CCl, like the the CLFs or something. But like it kind of it I don't remember how exactly it works. But if it's written there in your notes, just look at the equations and figure it out yourself. But the idea is that it allows the sulfur dioxide to proceed through a pathway that involves NOx itself. So the sulfur dioxide will be formed much easier compared to without the NOx in place. Yeah. So I think it does something with the ozone and all that as well. So I don't know. I have no idea. Okay, so the last one is the catalytic role of Fe2 plus in the iodine minus thiosulfate 2 minus reaction. Oh yes, this is my favorite thing. It's so fun to watch. Okay, it's an experiment that you probably might do for your kinetics as well. Yeah, this is probably one of the experiments that you have to do. Measure the time that it takes for the blue color to wait disappear or something. Wait, no, appear, or for sulfur to form and stuff like that. That kind of that kind of reaction, right? So how this happens is that the Fe2 plus can become Fe3 plus, then Fe3 plus can become Fe2 plus. So what we do here is the Fe2 plus will first if you go to your what page is this, 46, your electrode reactions, and you can see that wait, where's the one? Yeah, so Fe3 plus electron becomes Fe2 plus is 0.77. So you probably need to explain with the E naught as well. So mention the values for that. For iodine, it is 0.54, and for where was that? Thiosulfate. If I'm saying it wrongly, then pardon me. Where is it? I can't find it. Oh my gosh. 2.01. So for thiosulfate is 2.01. So what happens here is well, okay. Okay, so the iron 3 plus is more oxidizing than I2, I suppose. But that means that the iron 2 plus is is wait, I kind of forgot what happens. Sorry. Okay, so so iodine will become I2. So how that happens is that you need Fe3 plus to do that to the iodine minus. The Fe3 plus will require electrons, and the I2 minus will sorry I minus will give you the electrons. And and vice versa, if you're looking at the thiosulfate, the 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 thiosulfate is more oxidizing than Fe3 plus or Fe2 plus for that matter. So it will oxidize Fe2 plus while so that will first react, and then the Fe3 plus will then react with the iodine. So I'll just write down the equations here, and if I said something wrongly, I'll probably take note of that there. Yeah. Okay, so yeah, just mention which one is more oxidizing and which one is more reducing, and you can describe it pretty well. Okay, so the final thing to wait, what is there a final one? There's two more learning objectives. So the next one is describing enzymes as biological catalysts which may have specific activity. That's pretty much it. So enzymes are, well, bringing us into the realm of biochemistry, because even though they're like biological entities, a lot of biology is pretty much just macrochemistry. So like all the chemical molecules forming various structures like proteins, enzymes are also proteins, so do recognize that. So proteins and things like that. So enzymes are actually pretty cool. So they're made up of many molecules. If you have studied biology before, you might know how. And they can their job is to basically make reactions faster so that your body can do things faster and not like take forever to do certain reactions. And they're particularly specific because different enzymes are meant for different things, and this allows your body to have more control on what stuff you want at what point of time you want it and all that. So that's pretty cool. So how are they specific in the sense? Enzymes have a particular configuration. So like the way that the molecules are bonded will then form a shape, because in a protein chain there'll be some units that are hydrophobic and some that are hydrophilic. So these units are like peptides and wait, no, not peptide, amino acids. I mean, they are peptides, but the unit is a each of the units is an amino acid, and some of them are water liking, so they are hydrophilic, and some of them do not like water. They prefer the liposomes and things. Sorry, they prefer lipids, so they are hydrophobic. And because of that, enzyme will form a shape where the hydrophilic ones may stick out and the hydrophobic ones will be in the center. Yeah, so this gives them a particular shape, and not all molecules can fit into that particular shape. So the molecules that can fit into it will probably go in, and the fit will become better once the molecule comes into the enzyme and it kind of snuggles in. Yeah, so it won't be the exact shape, but a very close shape that will allow the molecule to enter, but not a lot of other molecules. And once that happens, the reaction can occur, and the products can leave because they no longer fit the enzyme. Yeah, that's basically how they work. Okay, so the molecules that go into the enzymes to react are called substrates. And now we have to see what's the relationship between the concentration of substrate and the rate of an enzyme catalyzed reaction in biochemical systems. Okay, so even though the body can produce enzymes many times, they won't produce like an infinite number of enzymes. They have a finite number of enzymes. So at any point of time, the like you imagine the enzyme like their activation site. So imagine them like a bunch of holes, and you have a bunch of ball like marbles or something like that, which will represent the substrate. So when the marbles go into each of the holes, they are there for some period of time, or at least a small period of time. But if your concentration of marbles is so high that they already saturate all of the enzymes, the rate will no longer be affected by the substrate concentration itself. So what this means is, let's say you start with one marble. So one marble, I mean, you can have multiple enzymes doing stuff on one marble. So one marble will only go to one enzyme. So when you increase the concentration at low concentrations of substrate, the rate will actually be faster because we have enough enzymes to take care of them. So there will be one marble, two marbles can be taken care of two enzymes at the exact same time, so the rate is doubled, and so on and so forth. But once, let's say you have 10, let's say you have 100 holes, and you're already at 100 marbles, and the rate is gonna be it'll finish the reaction at the same period of time as we did with one marble. But once you introduce one more marble, which is 101 marbles, that 101st marble will have to wait for all of the 100 marbles to finish reacting before it goes inside. And therefore the rate is at a plateau, so it cannot really change after that. So after a certain concentration of substrate, all of the enzymes are saturated, and therefore the addition of extra substrate will not change the reaction anymore. So, yeah, so if you imagine it that way, you can see how the rate remains the same once the enzymes are saturated. Yeah, that's pretty much it. That's all you have to say. Okay, great. We're done. So I hope you found this understandable enough. And if you found this video useful, please press the like button and subscribe. And, look forward to more episodes. Stay safe, study hard, do whatever you need to do. Yeah, if you want anything that I need to cover, then please PM me or comment below. And I will try to do it. Because, yeah, I should have time to do it now, indeed. Or if you have any other questions, you can ask me as well. So with that, I would like to say thank you and bye.